All right, so test begins this week. As such, lecture this week will be dedicated entirely to helping everyone feel ready for it, answering both study questions and even just homework and quiz questions as you're working on those. So the floor will be open to any kind of help or issue or inquiry you guys have. A couple of things I want to go ahead and point out that have been drawn to my attention. Namely, students have been finding mistakes I made on the practice test, or really my answer key for the practice test. So I'll go ahead and point a few of those out. In my answer to number 5, partway through, so the setup here is still what I'd recommend doing. In space, this is an orbit question, gravity acts as centrifugal force, fill in the two formulas for those two concepts. The issue came in when I copied in the mass of planet Earth. I wrote it correctly here, but one line down, I accidentally wrote a 6 instead of a 5. There's no good reason for that. I just messed up. And what that means for you guys is you should write the 5. The 6 is a mistake. And my answers here are just too big. The actual orbital radius should be about 13 million, and that will also decrease the height above the ground to about 6.7 million. So don't make the same mistake. I wrote the 6, that's my fault. These answers should be smaller. You can recalculate it if you guys want to, but these are wrong, technically. And I'm glad someone told me, because if I make mistakes, I want to fix them. Speaking of mistakes, this other one's a small one. Number 11, part D, I asked for force. The number's correct, but I wrote pascals instead of newtons. So if I ask for force, it's supposed to be newtons. Sorry again. Those are the ones that have been pointed out to me so far. Let me know if you find any more. So, what's on your minds? Yes.
Can you go over the torque question on the practice test?
Practice? Yes, I can. Torque, you said? All right, yeah. So here we've got, basically it's a balance beam, but it's more of the flagpole type, where the fulcrum is to one of the two sides. Oh, good, got it on here. There's 3 forces acting on this horizontal piece of metal. We got the weight of the sign itself, which points down, and it's applied right at the end of the flagpole. You've got the weight of the flagpole itself, which will be applied at its center. A uniform object, its center of mass is usually dead center. So the weight of the flagpole will act here, halfway down its length. And the third force is going to be the tension in this rope. But note the rule, only forces perpendicular to the radius can generate torque. So only the y component of this tension is going to generate any torque. That means that if you say figure out how much torque the rope needs to generate, only the y component is contributing to that torque, and you have to do a tiny bit of trig to actually find the total force in the entire rope. But in the interest of honesty, I'll point out that no actual trig made it onto the test itself. So you should know, practically speaking, only perpendicular forces generate torque.
So just stuff like that right there.
Yes, so like only the y component here is doing anything. Which means that attaching the rope like this is inefficient. This would be, you'd ideally just have the rope pointing straight up. Actually, really ideally, you tie the rope here instead, if I'm being honest. Pointing straight up, tied at the end, that would be the most efficient thing. But sometimes engineers have to make aesthetic decisions and work around the limitations. Anyway, as it relates to the math that I showed here, the first question was, what is the total amount of torque that the sign and the flagpole generate? Note that these two forces both pull down on this fulcrum, on the flagpole, and they are both going to generate clockwise spinning torque. If you ever want to make absolutely certain if a torque should be clockwise or counterclockwise, I recommend just physically taking your pencil, holding it where the hinge is, and then physically exerting forces on it in the same directions to see what direction it spins in. So physically holding the pencil at the spot of the hinge, downward pointing forces make it spin clockwise. So both of these are going to generate clockwise torques, and that is why I added them up and labeled them net torque clockwise. You've got the weight of the sign 1 meter away from the fulcrum, and then also the weight of the pole itself halfway down its length. So there's two of them here, and that determines the total amount of clockwise torque acting on this particular object. Does that go so far? All right. Now, part B asks, what must the tension in the rope be to hold up the sign? For this thing to be held in place, net torque must be 0. That means that the clockwise torques must add up with the counterclockwise torques to become 0. That means that they should be equal to each other. So there's a couple different ways you can state that fact. I went with setting total clockwise equal to total counterclockwise. We already found the total clockwise, so now we just need to figure out what rope tension generates enough torque to hold it in place. So we figured out the total clockwise torque. Now we need to figure out how much vertical force generates the required amount of counterclockwise torque to stop it. And just to show again, hold the pencil here at the hinge. If you push up, like the rope is doing, that spins counterclockwise. So the only thing generating counterclockwise torque here is the vertical component of the rope force. So clockwise and counterclockwise have to be equal. Plug in the counterclockwise found from earlier. The only thing generating clockwise torque is the Y component of tension situated 25 centimeters away from the hinge. And the Y component of tension has to be 784 newtons total based on where it is currently situated. If the rope pointed straight up, that'd be the end of it. Now again, I didn't put any trig on the actual test, but practically speaking, since the rope is tilted, that would only be the vertical component, and the rope would actually need a bigger overall tension in order to make sure its vertical component was the right size. So, no trig on the test. Again, the practice test is meant to be harder than the actual thing. And practically, if you're ever building something like this, just again note, only perpendicular forces generate torque, and that means that if you wanted this thing to be as efficient as possible, you tie the rope here and you hang it straight up. Does that answer your questions? Okay.
Can you explain why it was 0.5 again?
Yes. So this is the torque caused by the weight of the flagpole itself, because if the pole's center of mass is not supported, it would just fall by itself. So its own weight is generating torque right now. And that force, its own weight, is centered on the object's center of mass, which if I say the keyword uniform, will typically mean that center of mass is dead center of the object. So all of its weight is currently concentrated halfway down its length. And since it's 1 meter long, that position would be 50 centimeters or 0.5 meters.
Okay. So we always have to incorporate that if it's asking for the pole or the mass of the pole.
Yes, specifically if the object is not, if like the beam itself isn't being directly supported under its center of mass, then its weight does generate torque. That's true in this example, and it's also true, if you recall from lab, where we looked at torque, there were a few examples where the fulcrum was not dead center on the meter stick, And in that situation, the weight of the stick generated torque as well. Wherever that is relevant on the test, I have made sure to point it out and label it. And make sure you know all of the distances. Well, that's the buoyant force, correct? Yes. So, we have a palmetto log that is floating downriver. This particular log is going to have a density of 400 kilograms per meter cubed. A particular log has a mass of 2,500 kilograms, and it is floating down a freshwater river. First question, how do you calculate the volume of this log? Density is defined as mass over volume, so density equals m over v. We know the density, we know the mass, we can find the log's total volume. This would be about 3 of me sitting shoulder to shoulder, like standing shoulder to shoulder on top of each other. So that is the log's total density. Sorry, total volume, the total volume of the entire log before dunking it underwater. The next question is, if the log is currently floating in equilibrium, how much of its volume must currently be underwater? If something is floating in equilibrium, what does that tell us about the buoyant force acting on it? Equal to the force of gravity. Very good. If something is floating unassisted, and the only 2 forces on it are buoyant force up and gravity down, they must be equal and opposite. Log. You know what? Water level. And forces. Equilibrium implies net force equals 0, buoyant force up plus gravity down equals 0. And what I did next was buoyant force formula rho VG, plus the weight, so the mass of the log times negative 9.8 must be 0. Since this is a negative term, I'm just going to send it over to the other side. And this does give us directly buoyant force equals weight of log. So they're set directly opposed to each other. And this kind of canceled out the negative sign too, which is nice. Now interestingly, there's a G on each side, so I canceled that out on my own work. You can include it, but it would factor out eventually. Density fluid, that would be the water, not the log. So density of fresh water would live there, 1,000. We're going to solve for V object. That is going to be the amount of the log that is under the water. And after the G's canceled out, that would just be set against the mass of the log. So the amount of the object that is under the water is only 2.5 meters cubed. Which means actually most of it is still above water. Which makes sense. Water's density is 1,000 and the wood's density is 400. That's less than half as dense, so more than half the log is sticking out of the water right now. Question so far? All right. Next. How much buoyant force, what would be the buoyant force on the log if the whole thing was underwater? Because this is only true when this much is under the water. So this is kind of like the beach ball scenario. Normally only a tiny amount of the ball is underwater, and if you jam the whole thing underneath, it takes effort from you and the water's gonna push on it to try to throw it back out. So how much would the buoyant force be if the whole thing was under there instead? And for that one, wait, where did I put that one? So here, instead of the 2.5 that we found earlier, put in the whole volume. Note that the buoyant force is a lot. That's why wood makes very good boats. Whole lot of buoyant force currently acting on the log. Note that that would be more than the weight. The weight would be 2,500 times 9.8, so about 25,000. So more than double. This would eject, the log would very quickly eject out of the water functionally. But question D is then, how much force would be required to keep the whole log underwater? So that's the force pushing up on it, and then separately its own weight is pulling down. So normally it's just those two. The question is, what third hypothetical force would we have to add here to keep it down there? So again, with the beach ball, what force do you have to add to hold it under the water? So this isn't a 2-force equilibrium, this is a 3-force equilibrium. Buoyant force up, weight down, and then some third hypothetical force from us also pointing down. These three things have to add up to 0, and it tells us that this downward force would have to be an additional 36,750 newtons down to keep it down there, which is a lot. Does that answer? Does that help? I would say practically, since wood is very low density, wood is very good for making boats out of, and it takes a lot of force to keep the lower parts of the boat underwater. Like, if the boat started breaking apart, pieces of it would immediately rocket back up to the surface, and then you just got a big hole in the boat with nothing to fill it.
Number 7, it's just kind of a clarification.
Okay.
When you did the negative 45 minus 30,
Yes. The main point there is just to show that the two velocities point in different directions.
okay, so it's negative 75 because the ball was hit to the right and it was coming from the left. Or
Yeah,
either way, but
I didn't really specify positive or negative for the velocities in the text of the question, but it says that the initial speed of 30 meters per second goes towards the batter, and then the final speed is 45 meters per second back towards the pitcher, which would be away from the batter. So we go from, for example, 30 to the left to 45 to the right. So that would be a change of 75. You don't necessarily have to make it the same sign, as long as you indicate somehow the direction changed, so therefore it's a magnitude of 75 and not 15.
That example we did in the notes, with the ball rolling down the ramp for, I think it was angular
Kinetic energy, I
kinetic
think.
energy.
Yeah.
How well do we need to know that?
The test is finalized, and looking at said test, there is a question involving angular kinetic energy, therefore the object is spinning, but It is not about the object rolling down a hill. It is not about energy. Like, it's just not factored
It's
into
just-
an energy conversion question. So
Alright.
specifically, I would, hold on, trying to say things in terms that don't give the entire game away. On the practice test, angular kinetic energy is factored into question 8. This is a little better representative of how it would be on the test. So here it's just calculating total angular kinetic energy levels both before and after a change and comparing the two. So this would be a better representation. You need to be able to calculate kinetic energy, angular kinetic energy level, but in the interest of honesty, the question where that comes up does not involve an energy transformation rolling down a hill. So you have to use the formula, that's the main thing, yes.
So I know how you said there won't be any trig on the test.
Yes.
Is there anything that goes the opposite way? Like, was there anything not on the practice test that will be on the test?
If it's
Any
on the test, it was on the practice test. I always try to make this longer and more difficult for the sake of it being practice and for the sake of you getting your mistakes out of the way here.
So if you did the practice test, you've seen everything that will be on the test.
Yes, now admittedly, again, the questions won't be exactly the same. Like, the buoyant force question isn't gonna be a log, it might be a piece of metal completely underwater or something like that, so same techniques, same formulas, but different situations. In the past, I've had students, like at the beginning of the course, when students are still getting used to things, I've had students complain that like, a test question might say something like driving a car off a cliff, and they'll say, we never did a car driving off of a cliff, but it's still projectile motion, like launching a marble out of a cannon. So, same genres of questions, but some of the applications might be tweaked and some of the flavor text will be different. Because for every question, I have to give you a little bit of context. You know, floating log, submarine, something like that. So, let me try to answer the question again. All of the formulas, general question types, and information you would need on the test are present here, but this had more questions and more things needed. Like there was like 1 or 2 trig things on here, but no trig made it onto the test, for example. Is that comforting? That's my goal anyway. I'll also try to say, as in an attempt to be comforting and assuring, mute projector. I've been adding any possible conversions and things that you might need and just leaving them on the board. I try to include them in the questions, but sometimes I take for granted that I have these memorized and not everyone else does when I'm writing things, so they're just gonna live here all week. Yeah, again, lecture this week is gonna be focused entirely on study sessions, or, you know, any random thing that pops into your head. If you don't have any questions, you are more than free to just leave. Like, you're always free to leave class, I'll never stop you. But this week in particular, if you've got everything you need, you can head on out.
Are we
I'll be
gonna-
here all week, helping anyone who does show up.
Are we gonna meet for lecture next Monday?
Yes, next Monday there will be lectures. That's the day I'm gonna give you your test back and graded, and then just done and dusted before the break. So you don't have to worry.
Sounds good.
So, do make sure you show up next Monday. The rest of lecture this week is optional, pending you have any questions that you want to talk about. And that includes homework. You can come in and just work on homework if you want.
And you won't be proctoring today, will you?
I do not, yeah, I won't be proctoring today or tomorrow, but, Dr. Edwards will, like, what am I trying to say? He'll be here, he knows the same stuff, and, you know, I've instructed him to answer your questions the same way I would.
How many people showed up last time on Monday? Do you remember?
I don't remember.
It was a little mini. It wasn't like crazy. It wasn't like packed. It was a few, and there were some people that
Friday was.
weren't in our
There was a
class.
good many on Wednesday too.
Friday was packed.
There wasn't an open seat in here Friday.
Some people just choose Monday to get it over with, and some people have to do it Monday for scheduling reasons.
I'm just glad there's no trade.
Me too.
Well, it will be on the final, so it's not gone, it's just temporarily absent.
Appreciate it.
I did have a question. The week after Thanksgiving, I'm not gonna be able to come to lab that Wednesday.
Okay.
So can I just come another day? Or?
Mhm.
Okay.
Yeah, absolutely.
Yeah. Okay, thank you.
You're welcome. And remember, every day except Thursday.
Every day.
So that's the only day you can't show up.
Okay. Thank you.
Welcome. Somehow after 3 years, still trip over that cord. Anything on your mind?
Other than registration, not really.
Oh, is that happening now?
Yeah.
Yikes.
It's not looking good.
Uh-oh.